We march on through Math 222, Calculus 2. On today's show, a very brief look at what we call relative rates of growth. It will really be, for us, pedagogically speaking, an opportunity to look back at L'Hopital's rule, but there are some other applications in some other disciplines that we should consider. So, here's the definition. We're going to let two functions, f and g, be positive for large x. And that simply means if you go far enough to the right on the x-axis, both functions are positive and they stay positive. This whole concept gets much more difficult if that doesn't happen. So f grows faster than g if the limit as x approaches infinity of f of x over g of x is infinity. So if I put f over g, look at large values of x, and I get infinity for that limit. I get that limit can be made arbitrarily large. Then f grows faster than g. F and g grow at the same rate if the limit as x approaches infinity of f of x over g of x equals L for some finite L not equal to 0. We should pause for a moment and consider the following. Oh, go magic pen. Why L not equal to 0? Well, what if L were 0? What if, oh, back to regular pen. What if I had the limit as x approaches infinity of f of x over g of x, and that was 0? What would that mean? Pauses to consider. Well, if f over g is 0, what would that be? If f over g goes to 0, then g over f would go to 1 over 0. Well, that would go to infinity. And what does that mean? Well, that means that g grows faster than f. So if you're in the scenario where f over g is 0, that means that g grows faster than f. And that's why we have to have this idea here that, oh, that's terrible. That's why we have to have this idea here that the limit L cannot be 0 if f and g grow at the same rate. And so, time to play everybody's favorite game, who grows faster? Who grows faster? Now, we both know that e to the x shoots up like so, and x cubed shoots up like so, but what happens as x gets really, really large? Does the blue go back and overtake the red? How does that go? Well, if we take the limit as x approaches infinity, e to the x over x cubed, we realize that the numerator heads to infinity and the denominator heads to infinity, and so we will try again. This is the limit as x approaches infinity of derivative numerator over derivative denominator, and we recognize that this goes to infinity and this goes to infinity, and so we try again. Derivative numerator, derivative denominator, this goes to infinity, this goes to infinity, and just about when we're out of space, we say this goes to infinity, this goes to 6, that's infinity. So who grows faster? e to the x grows faster. And that's exactly what happens. The blue function overtakes the red function and stays above the red function forever and gets farther and farther away at faster and faster rates. That's a key. Once the blue function overtakes the red function, it gets farther and farther away, and the way it gets farther away is growing. Because this is going to happen, and you're going to say to yourself, well, I know how this goes. This is 2x, and this is x, so obviously 2x grows faster than x, right? Except when you play this game, guess what that is? You're right. I, like Dora the Explorer, assumed you just said something. This is a limit that is not 0 and it is not infinity, which means that these functions grow at the same rate. Now, obviously, 2x is above x from this point forward, but the way in which 2x is getting away from x never changes. That is constant. So hopefully that's helpful. Hopefully. Maybe. I don't know. That's an interesting question. Well, that's interesting. And that's interesting because we could take derivatives on top and bottom, but each time we'd just have we'd have the same issue and this thing here, and what do we do with that? And I mean, we could keep going. That's not helpful. Maybe it's helpful not to use L'Hopital at all. Maybe it's useful just to take a look at it like so. Because I think I know what happens to this as x gets large. I have some number in here that's greater than 1, and I keep raising it to larger and larger powers of x. That keeps compounding. That goes to infinity, which means that 3 to the x grows faster. Hopefully that makes sense. Hey, a couple of things for you to consider. Just a couple of really quick OYOs, and that's on your own. Who grows faster, x cubed or ln of x? That doesn't take a whole lot of amazingness to think about. Who grows faster, ln x or radical x? Who grows faster? Those are interesting questions to think about. This is probably a little more difficult to see, and so you need a limit to figure that out. Okay, that's the basics. That's the basics. And that's all I'd really like to walk you through in this section from Thomas, From Beyond the Grave, leading us toward the end of Chapter 7. Okay, so there you go. You've got some work to do. I'll see you in class. And there it is. Bye.